right. Well, we can start. Themis, can you hear me? Back?
Yes. Yep.
Oh.
Yep. Loud and clear.
Fantastic. So, so this is the last talk for today for the deep dive in data-driven fluid mechanics, which is streamed on YouTube and Zoom. And we have now the pleasure to have Themistoklis Sapsis, who's a professor of mechanical and ocean engineering in the Massachusetts Institute of Technology. Hi there. And he's going to talk about extreme events, model selection, and the value of data. So Themis can hear us, and we can interact with him as if we were here, I think. Okay? So it's a formal talk, and people might interrupt you informally. Okay?
That would be great, of course. So thank you and for organizing, Luca, and apologies for not being able to be there physically. So I want to give an overview of our recent work on the modeling, the probabilistic modeling of extreme events in complex systems. And in particular, I want to discuss some recent developments in connection to machine learning representations and also the value of data for modeling of extreme events. So I want to begin with some motivation. And my background is applied mathematics and ocean engineering. So as an ocean engineer, I'm interested in problems related to resilience and reliability. On the left, you see a coastal region subjected to extreme waves. And on the right, extreme ship motions of a ship. I can tell you that especially for the movie on the right, the surrounding seas are not so bad to cause this sort of bad rolling effects. It's primarily nonlinear dynamical mechanism, parametric rolling in particular, that is causing this sort of situation. So what is the challenge? The challenge with this problem is that we have typically some set of random parameters, or this can be random boundary conditions, forcing excitation, and so on. So all this source of randomness, and again, this is not perturbation type randomness, this is like order one. So we can collect it as a random vector. Here it's a random vector describing waves. We typically have over the decades, science and engineers have developed, very accurate modeling tools or even experimental techniques to be able to predict quite accurately what is going to be the quantity of interest for a specific input, right, for a specific X. But this is a very expensive process. F is a very expensive thing. You don't want, in general, to repeat it, thousands or millions of times because it's expensive. However, if you are interested to get the statistics of the quantity of interest, and this is meaningful given that X, as I said, it has like important stochasticity, this becomes a non-trivial problem, right? So the goal is to find the probability density function for a quantity of interest, like the structural response or the specific motions. And for this specific problem, I'm giving you a sense of what that means, right? We have this ratio R, that is the time for computation, divided by the time interval of the computation, right? So the numerator is essentially the wall time with a single processor, or even with more than one processor, and the time interval of computation. So if you are interested to, for 3D CFD, this is order one, right? Potential solvers, of course, it's much lower. But keep in mind that when we study reliability problems, fatigue, we are interested on time scales of 100 to 1,000 years. In fact, insurance agencies, they're interested for 100,000 years. So it's quite expensive to do these computations. And it's even more when you try to optimize problems, to do risk-averse optimization and so on. So this is one area I will be expanding more and see what we can do. The other topic that I will mention a few things is about designing rigorous mitigation measures for climate change, and this is obviously a big problem. Why is it a big problem? Because, well, there is good understanding from policymakers on what is going to be the effect of certain policies on the emissions. The link that connects emissions to climate response, it's a very hard problem. And it's a hard problem because climate models are expensive. Of course, they're hard to simulate. Climate is a very hard problem, obviously, but beyond that, it's also very expensive, assuming you have, an excellent model. So here I'm showing you the effect of low resolution, right, on the right. So you see this is the density plot showing hurricanes, tropical cyclones in particular, and extratropical cyclones. And this is the real data, right? This is reanalysis, if you want, ERA5 data. And this is what you get if you run quite accurate atmospheric model for the same duration, and with a decent resolution. So 110 kilometers resolution is actually quite good, but not for resolving storms and hurricanes. So you see that we are more or less missing everything. And so there is a need to try to compensate about this, given that, again, if you try to run like 3 kilometer resolution, which is probably what you need to get the densities right, we're talking in the biggest supercomputer right now of like 2 simulated years per day, right? So it's extremely expensive. And then the last thing I want to talk about is about how we can apply some of these ideas of optimization in complex fluid flows, maximize mixing and drag reduction. Again, in this case, the X is the control law, and the output is some quantity of inverse drag or mixing. And so the goal is to do optimization with the same sort of ideas, meaning with the minimum number of experiments, how can we get the optimal configuration? So we are going to use, of course, there is a plethora of tools that people have been using to do these sort of things, especially optimization and UQ. Most of these ideas rely on either developing a reduced order model and try to work with a reduced order model. Of course, for optimization, there is a huge literature, right? It's impossible to even summarize, but like adjoint methods, all sorts of tools that have been very well developed. Here we are going to build on this active learning paradigm. Essentially, the idea is the following. Again, the special twist for us is that we are trying to minimize the number of computations or black box evaluations, right? Either this is an experiment or CFD simulation. So we start with some initial data, X, Y, right? X is the random vector, as I said, Y is the associated output, possibly noisy. We need a probabilistic regression method, and the golden standard here is Gaussian process regression. The problem with Gaussian process regression, as we will see, is that it does not scale very well for high dimensionalities, more than 5 or 6. So we really need to adopt something more robust, although we will have to sacrifice a lot of theoretical understanding. So we need, in any case, we need a probabilistic regression method. And as I said, this is essentially an interpolator, but with good a priori estimates of the epistemic uncertainty, right? What is the effect of having few samples, basically? So this is the next step, assuming we have some data. The next point is using the probabilistic regression to select the new experiment, the new input. And this is where we have done a lot of work on developing acquisition functions with guaranteed optimality properties. I will spend some time on this. And after we have the new input, using some criterion, the acquisition function, we perform the new experiment, either an actual full experiment or as a computational experiment. We complement the initial data. We repeat this loop until our model is good enough, meaning the surrogate model, to either do UQ or optimize. So this is the general idea. Now, acquisition functions, I will mention more things later about the probabilistic regression step, but as I said, the key thing when it comes to extreme events is how do you choose your experiments? How do you design good experiments? And interesting enough is that the criteria that we will develop, they have a lot of value even for problems outside extreme events. So the acquisition function, as I said, you can see here, we start with the probabilistic regression, and we add a new hypothetical point. Let's call this X star, that can move left and right. It does not change the regression because, again, we don't know the exact output for X star. It's a hypothetical point, so the best we can guess is what the regression scheme gives. But what changes every time we add a new X star is that the confidence bound or the error bars are essentially going to zero, right? Again, this is all hypothetical, assuming we have this point. So under this assumption, we can start building criteria on how to do that. So the obvious one is uncertainty sampling, right? We just add X star to the locations where you have the highest uncertainty, epistemic uncertainty in your regression. The next one, I mean, less obvious, but it's the obvious next step is the integrated variance reduction. Essentially, you're adding the point X star, or you're choosing the point X star so that the integral under the modified confidence curve is minimized, right? And you also weight according to the probability density function of the input, so you can exclude, exotic X's, right? Things that have very low probability of happening. Mutual information is also a very popular one, and there are important reasons why mutual information is not very practical. Number one is the computation of it. And number two is that as sigma, as the overall variance goes, becomes smaller and smaller, you can show that the mutual information essentially behaves exactly like the integrated variance reduction. So asymptotically, it's more or less the same thing. What is the key pathology, though, of these criteria that, again, they have been very popular in various areas? The biggest problem with all this is that, as you can notice, on the right-hand side, there is no participation of the output Y, of the Y values, right? So sigma n is the uncertainty, and the uncertainty, especially in Gaussian process regression, you can write down the formulas and you can see that uncertainty has no dependence on the output values, on your output data. Now, this is very dramatic, actually, because when we are studying extreme events, the output value is exactly what we are interested in. So if we ignore, the output, we are missing more or less half of what we are interested in. So motivated by this observation, if you want, and of course our physical understanding of extreme events in fluids, we essentially, what do we have in fluid dynamics? We have a turbulent flow, right? It's essentially a dynamical system that spends most of its time around this shaded region. And once in a while, it undergoes these green islands that cause an instability and then an extreme event. So if you try to sample this space, obviously, you don't want to sample only according to the probability of X, right? Because it will just send you in the core or in the neighborhood of the shaded region. You also want to include the value of Y, or the expected value of Y. And this is the key thing. The way we did that is to start thinking in terms, instead of thinking only in terms of the map itself, which is what I had just been discussing, we start thinking in terms of the induced probability density functions, right? So every map, like the regression, Y of X, since you have a probability measure for X, you can translate that into probability density function for Y, right? So the blue curve, which is the mean regression, it will give you the blue density, PY bar. The red curve, like the upper bound, if you want, which is the upper dashed line, it's essentially the mean estimation of your model plus beta times the standard, the estimated standard deviation. It will give you another density, right? PY bar plus. So instead of thinking on convergence on the left, we start thinking on convergence on the right, convergence of the output densities or the densities of the quantities of interest. So this is a criteria we introduced back in 2018, and essentially we're choosing the next point, X star, under the requirement that the distance between the perturbed model, the red one, that is the model, the PDF associated with the mean estimator plus one standard deviation, minus the PDF of the mean regression model, this should be as close as possible. And we use the L1 of the logarithms of these PDFs so that we can emphasize the tails, right? That's what we're after. So this is a criterion, as I said, that actually worked quite well. Why? Because the PDF of the output, as you can see here, by trivially writing a conditional PDF argument, you can show that it depends explicitly both in the input PDF, but also on the estimated model that you have from the data you have so far, right? So the information for the model, meaning the input-output relationship, is explicitly encoded into your selection process, into your criterion. This is not like the red piece is completely missing from traditional criteria. So at that time, we applied this into a problem associated with an offshore platform subjected to random waves. Essentially, we started with a Jones-Swap spectral density. We parameterized the waves through a two-dimensional parameterization. Essentially, we computed wave groups associated with length scale, specific length scale, and the specific amplitude. Each spectrum is eventually connected to a given PDF for the wave parameters x1 and x2. So in this way, we have made the problem finite dimensional. And so the whole idea is, how do you sample this two-dimensional space, right, in an efficient way? For the experiment, we use smooth particle hydrodynamics, quite an expensive thing. So we didn't want to run too many experiments. And we applied the idea I just described, and we were able, with just actually 15, 16 experiments, to get the PDF for the structural loads quite accurately up to 3 standard deviations, right? So the dashed line is 1 sigma. So what was the, okay, this again, we were very happy about the outcome because 15 simulations is actually not many for this problem. But what is the limitation of this approach? The limitation is that the criterion you see on the bottom, which is the one we build on, is not easy to compute. It's not easy to optimize, right? So it's good for dimensions up to 2 to 3, actually. The problem is that if you move to irregular C states, realistic C states, broadband Cs require at least order of 10, 20 modes to be described accurately. You cannot just use two-dimensional wave groups. So the question was, can we derive an alternative acquisition function that is appropriate for high dimensions? And the answer came a few years later when we were able to prove an upper bound, a rigorous upper bound for the quantity, the criterion that I just described. So on the left, you can see the L1 distance between the two PDFs, the one from the perturbed model and the mean model. And you can actually show that this is always bounded from this weighted integral of your variance, the epistemic variance that you obtain from your regression model, probabilistic regression. So this is weighted according to the probability density function of the input, and which is, again, what you have in the numerator is the standard integrated variance reduction term, nothing fancy. But the key thing is that now you have an extra term in the denominator, right? And I will discuss more about this. So why this is a good criterion? First of all, it's easy to compute its gradient in high dimensions, right? Because eventually X star appears only in the variance, and that's not hard to do, especially if you're dealing with Gaussian process regression. Everything can be worked out analytically. So you can apply gradient optimization techniques. It has a lot of advantages. Now let's focus a little bit on the mechanics of the new points, of selecting the new points, why this is a good criterion. First of all, we have, of course, the error, right? That comes from the probabilistic regression. As I said, this is weighted according to the probability density function of the input. So we are not spending resources on inputs that will never appear, right? But how does this measured? Well, it has to be balanced by the probability density function of the output. So you see here on the denominator, we have the probability density function of the output computed on a specific, associated with a specific input, right? So every input X is associated through the model we have estimated to a probability to an output Y. And the overall weight is 1 over the probability of Y. So what this extra term does, which by the way, it comes out naturally from the bound that we derive, is that it emphasizes inputs that lead to large outputs, right? Those that appear rarely. So the error is penalized in a non-uniform way so that high probability inputs are emphasized, but also low probability outputs are emphasized. And this is done in a balanced way. That's why we call this the likelihood weighted acquisition function. So the next thing we try to understand, we ran a few applications. We saw, that this is indeed very successful. And we try to understand, though, how close this upper bound is to some notion of optimal, right? We wanted to see optimality. So the question is, how do you define optimality in this context? So we defined the best possible choice of acquisition function for a given map Y. Obviously, it's going to be the X star that will bring this L1 distance as close as possible to the exact map, right? To the PDF produced by the exact map. Of course, the problem is that we don't know the map a priori, right? So how can we define optimality in an a priori sense? Well, we do that by defining the selection criterion as follows. We are minimizing over X star, or we are picking the experiment that will minimize the supremum of all the functions that satisfy the data that we have collected so far. In other words, all the functions that interpolate the data we have so far. So over all this space, we take the worst case scenario, right? So you see that on inside the supremum, we have the L1 distance of the PDF of our regression minus the PDF of Y, where Y is the worst case scenario within this space of functions that satisfy the data, right? So we have the optimality, if you want, condition. It is associated with solving this minimax problem, which of course it's a completely intractable because it's defined over a functional space, but nevertheless, it gives us a way to define optimality. So the question is how close we are to this condition, right? And the answer came a few, 1-2 years later, when we were able to actually show that, at least in the context of Gaussian process regression, where a lot of things can be done, like there is theory, you can show that this supremum that I just wrote, it's exactly equal asymptotically, meaning for small sigma, it is equal to this weighted version of your epistemic uncertainty. So you see that we have, again, as we had previously in the criterion we derived as an upper bound, we have the probability density function of the input. So this appears, but we have also these extra terms, and the probability density function of the output appears in the denominator. So it's slightly different from what we derived as an upper bound 2 years before that time, but it's close, at least in terms of form. In fact, we were able to show that a Cauchy-Schwarz inequality is essentially the step that can take us from the optimal criterion to the upper bound we were using. So the answer to this question of how close we are to the optimality, essentially it's a Cauchy-Schwarz step away. It's not very far. And of course, this is in the sense of asymptotic optimality, meaning for small sigma, right? For larger sigma, things are harder, but feasible in the sense that you can derive higher order expansions of this criterion, this optimality criterion. We have not done this yet, like we are in the process of doing it. It is important for problems associated with tipping points, discontinuities, and these type of things. Now, why not using the optimal criterion? We're using the one that is coming from Cauchy-Schwarz. Well, because sigma is harder, at least in the context of GPR, it's harder to optimize compared with sigma square. And that was the only reason, right? Practical reasons. And again, the difference we've seen, it's super small. So with this understanding, I want to now jump into some problems to demonstrate better, the value of these ideas. So the first problem is to quantify risk in a dispersive wave model for weak turbulence. This is the Maida-McLaughlin-Tabak model, the MMT. It's essentially a dispersive wave equation. This is a pseudo-differential operator associated with deep water waves. Nonlinearity is the same with standard nonlinear Schrödinger, and then we also have a selective Laplacian term that kills, the very, very, very high wave numbers when you get an extreme event because of the interactions, the nonlinear interactions in this system. This will eventually grow in an unbounded way, so you want the high wave numbers to eventually be dissipated. So this is the selective Laplacian that is dumping above a certain critical wave number. So if you run this system, this is what you get. You see the space-time snapshot, and you have the sporadic occurrence of these extreme events that you see here. And our goal is to try to capture the tails of this system with the minimum number of simulations, right? So this is the statistics that we are after, or if you want the magnitude of these statistics of this response. So here I'm showing the real part of it. So heavy tails you can compare with the Gaussian core. And let's see how we can apply the framework I just described, right? There are certain steps, additional steps. First of all, we have to represent the stochastic initial conditions. We start with Gaussian initial conditions. We expand into a coherent wave expansion, and we keep certain number of modes. Theta is the number of modes we maintain. To represent what is going to happen, like after finite time, we move away from Gaussian progress regression because simply Gaussian progress regression doesn't scale very well. And here theta needs to be higher dimensions, like we work with 20 dimensions here. So Gaussian progress regression has no luck on this regime. So we're using a simple idea. We're essentially adopting this deep operator neural networks. There is no, our framework does not really depend on DeepNet or a standard neural network. You can use any your favorite architecture, as long as you are confident that captures well the system. So we are using though an ensemble of a neural network. This is important because the ensemble allows us to estimate the epistemic uncertainty to a certain degree. So we are essentially, for the same data set, we are training multiple times, not many, multiple times the neural network with random initial weights. And that gives us not only an estimation of the quantity of interest, in this case, it's the real part of, the maximum, the spatial maximum of the real part of the response, but also it gives us the uncertainty estimate, right? Our goal is to reduce the log PDF error, what I described before. Essentially, we're interested to capture the tails. And here, just for visualization purposes, I'm showing you the situation where we have just two modes in the initial conditions, right? So very simple problem. On this panel, you see the trained deep neural network model that we obtain. Log of sigma is the term associated with the uncertainty of our estimation. So this is exploration term. Exploitation is log of W. W is the weight between probability density function of the input versus probability density function of the output. And then the acquisition function is their product. So, and of course, the output PDF is shown on the bottom. So you can see that it's essentially just less than 10 iterations, just 10 initial conditions. You see how these are chosen. We have very good convergence of the PDF. And of course, this continues, and you see how the samples are being collected in a non-trivial way that weights not only where the model has uncertainty, but where the output is important. So we, of course, scale up to higher dimensions. This is for 8 dimensions visualized through multidimensional scaling. Again, you can see that with a very small number of iterations, less than 20, 30, we have very good convergence. More interesting is the pattern that we obtain. Again, this is an unfolded 8-dimensional space in 2 dimensions. And you can see how the pattern picks, I mean, the acquisition function pick points at the core of the system. These are points with high probability, the everyday points, but also explores these winks that you see here associated with extreme events. So there is, like, beyond the speed of convergence, there is one more thing, and that shows up in a very severe way if you go to higher dimensions. Higher dimensions, like exploration in high dimensions, is obviously a hard problem. Here we pushed to 20. In fact, we also did 60 dimensions, but I will discuss about 20 now. And I can explain later why not 60. But like for 20, we try to compare the performance of the reduced order model compared with a situation where someone knows nothing about active sampling. They don't want to know anything about active sampling, and they just do structured sampling, right? Latin hypercube sampling is the most is the vanilla version of structured sampling in high dimensions. So if you do that, the error actually gets worse as you add more points. And this is not, well, it may be paradox, but it has been documented very well in numerous studies. This is the so-called double descent problem. Like the training becomes worse and worse and worse until after a long time, until it starts getting better, right? And this has to do with the fact that your model is putting emphasis in the wrong places, so it misses the actual points. And the more points you place in the wrong places, the less emphasis is given to the important regions. Like that's a very high level, if you want, description of what is going on. So you see that this is pretty bad. Surprisingly, if you do active sampling with just emphasis on the epistemic uncertainty, on minimizing the uncertainty model, you also get the same behavior. So the green and purple curves are exactly showing that. Like this is associated with active sampling driven by uncertainty, right? And the two curves are different because in the first case, we start with a very small number of Latin hypercube samples. In the second one, just randomly picked some samples. So it's the effect of the initial points, if you want, the two colors. And then we did the likelihood weighted approach that I just described. And you see very nicely how we have monotonic convergence. And again, why this is happening, this is not magic. It's because, if you see on the right, we have to see what type of initial conditions are chosen according to its criterion. So if you do Latin hypercube sampling, the only way to capture extreme event behavior is to have extremes in your initial conditions. The curves that you see, the color of the curves are associated with the eventual value after finite time. So you see that the curves that are already big initially, they are the darkest. On the other hand, you see what is happening with the likelihood weighted sampling. Likelihood weighted sampling, it does not pick initial conditions that are already big. It's picking initial conditions that are initially small and eventually become very big, right? And this is if you want, the success of this idea, it's exactly hidden in this result. So, as I said, this eventually creates the types of convergence that you see on the left. And we also have, certain events, like this is one of the events that you observe here. You see how the black curve is the initial condition that if you notice, like there's nothing interesting about it, but eventually after finite time, it becomes an extreme event. This is, again, the key thing. So we applied this to problems of, with higher practical applicability. I mean, we love MMT, but the Navy is interested in quantifying extreme motions and loads for ships. So we were able to, extend what we did in 2018 in 2 dimensions. Now we are able to run 10, 20 dimensions, essentially representing stochastic seas with a coherent wave expansion. Keeping 20 modes is sufficient to represent most of the important situations. We represented the output, in this case is the vertical bending moment, through also a coherent wave expansion. And so the whole problem becomes finding the map from the space of coefficients describing waves to the space of coefficients describing time series for vertical bending moments. This is the Q I of alpha. Alpha, again, are the coefficients for waves. There are certain technicalities associated with this problem that I don't want to spend a lot of time, and these are associated with a finite time horizon. How do you choose the duration of the wave groups? And this is a challenge, because if you choose too small, then you are missing transient dynamics associated with the memory of this system. So you have a lot of uncertainty on your output. Your Qs become uncertain, inherently uncertain. This is not epistemic, this is aleatoric uncertainty. If you increase your duration, then you need more modes, you need larger, higher dimensional alpha. And of course, this increases the epistemic uncertainty, makes the problem harder. So in any case, there is a nice optimal there on the duration of the wave groups. And you can, again, with very few samples, you can see with 44 wave groups, we can eventually capture the black curve is the vertical bending moment, the peaks of the vertical bending moment for, you can capture it with just 44 experiments, right? So this is, again, this is quite an improvement. The black curve is based on literally hundreds of thousands of hours of simulations. Like, this is very expensive to obtain. So the next thing I want to discuss is about the climate problem. And the reason I include that is because it is fundamentally different from engineering problems, not only because of the scales, but because of the most important thing. You cannot choose your data in climate, right? There is, a certain past, it's one realization, and you want to build probabilistic models. So there is no way you can, in principle, one could say, okay, I will design optimal initial conditions to run my climate model, but good luck, like, these are expensive things. It's not easy to convince anyone to allow you to run a climate model, in an optimal experimental design sense, at least not yet. So we focused on a different aspect, and that was the following. Like, in these problems, we have terabytes of simulations, like, and reanalysis data, thousands actually of terabytes. How do we value this data? So the question is different now. We are trying to value the data and perhaps pick the most informative data out of a vast data set, instead of what we did previously, where we tried to find the statistics of the vertical bending moment with just 40 simulations. So this is the main idea, and again, I mean, there are certain steps, so I will try to describe carefully, what we have done. The overall problem from the climate point of view is how we can use few years of storm resolving simulations, right? These are very expensive 3-kilometer resolution simulations, to machine learn a correction operator for core scale models, right? So I already discussed why the core simulations, they are very limited. And the question is, all right, from the bottom simulation, can we apply, or can we machine learn a correction operator that will take the output of this model and will make it behave, or will improve its overall statistics, right? Hopefully will make it look as the ground truth. And in order to do that, of course, as I said, we need storm resolving simulations. But this is not, an out-of-the-box supervised learning problem, simply because the two data sets, if you take two data sets because of chaotic divergence, these two things will be completely different. So this brings us to the core of this idea. As I said, if you take an initial condition, let's say this is the attractor for the climate model, right? Obviously high dimensional. Let's say this is the reference trajectory, the red one. This is your reanalysis data for the last 40 years. And this is your course result trajectory, right? This is what you get if you run 110 kilometer resolution. And obviously this diverges pretty rapidly. There is no expectation to be close. The question is, can you learn something useful from the reference trajectory to correct at least the statistics of the course trajectory, right? We're not expecting to get accurate description of the course trajectory over small times, but at least the statistics should be improvable. So this is our goal, to machine learn a correction operator from course scale solution to the reference. Now, in order to do that, we came up with this idea of instead using, the two trajectories I just presented, meaning the course, this is the green here, the course result trajectory and the reference trajectory. Instead, we are running the course scale model. This is the course scale model on the upper left, right? Just a dynamical system. We are running it with an extra term. It's a nudging term. This nudging term, the only thing it does, it tries to keep the course scale simulator close to the reference trajectory, right? So you get the black curve that you see here, that again, it is trying to keep the course model as close as possible to your reference trajectory. Obviously, this is not fair, right? Because if you try to run future projections, you will not have the fine resolution simulation or the reanalysis data. Well, we do that only for training. So we are training a map that takes as input the black curve, the nudge trajectory, and provides as output the target is the reference trajectory, right? Again, we are using this nudge data set only in the training process. This allows us to do what? To machine learn a correction operator that is able to fix the course simulation over short periods. We are not interested for long time deviations eventually, because our goal is to capture statistics. So we are trying to see if, a specific storm in the course model should actually be accounted as a bigger storm in reality, right? This approach will not tell us how often a storm is happening. It will try to fix the magnitude of existing storms. And again, our goal is to quantify statistics. That's how we are thinking. So this is the idea. We apply this nudging technique in order to improve, to machine learn a correction operator that takes us eventually free running course simulations and transform them into high quality outputs. There is, several details on the architecture, on how we do that, but in more or less we are using a series of convolutional neural networks, right? We have a latent space. In the latent space, we are also including LSTM, so we can incorporate memory effects, and then we do the deconvolution. So the first step is to see how that approach works in the case of events that have not been included in the training, right, but have actually happened in the past. So top plot is the era 5, and this is for Hurricane Sandy, right? Era 5 is the ground truth, if you want, or reanalysis data. The bottom row, the second row is nudge data, is what you get if you just try to solve in a course simulator and nudge your time series. If you want, this is the unfair approach. And then the LSTM is essentially using the nudge data set and corrects it, right? The way we are discussing. Again, this is for validation. It's not future projections. So you observe that the error is noticeably improved by applying this neural network operator correction to your data set, right? So you can see here a snapshot. So this is again a sanity check. It's not like new results, although one can use it to do data simulation, right? So if you do run data simulations, the data simulation, you can use your nudged simulator or nudged output and simply pass it through the trained neural network, and that will immediately improve things. Now, let's see now how things work in terms of the statistics. And everything you see from now on is using the trained operator and core scale simulations that know nothing about reanalysis data, right? So there's no nudging here. As you can see here, we are just running a core scale data set, the 110 kilometer resolution. We just run it for 40 years. We pass the output through the operator that we machine learned, and then we compute statistics and we compare with the ground truth, which is the error 5. So here you see the results. This is for UNV velocities, temperature, and humidity. And the first thing you note is that the dashed line is the unprocessed or the core scale output, the raw core scale output. And of course, you are missing a lot. The black curve is the reanalysis data, and the blue one is the one we are getting from passing the core scale simulation through the neural network. And you see noticeable improvement, especially at the tails. The tails is what we are after, right? So temperature, we have some severe underestimation of negative extremes for temperature. This is fixed very nicely from this neural network operator. Same thing with humidity. We're able to fix certain overestimation, and the velocity is also getting fixed. So we also apply this for integrated vapor transport, and here you see, and other things like tropical cyclones, and you can see again the noticeable improvement. This is the difference between error 5 statistics, time average statistics of the integrated vapor transport minus the core simulation. And this is what happens if you pass this core simulation through this neural network that we trained, right? And you see the noticeable improvement. So doing all these things, I can tell you that this is a very expensive thing, right, to do. Whenever you work with climate data sets, you need a really big infrastructure to run these problems. So this, to connect it with all the previous work, this question of what is the most informative data came up. And so we decided to try to evaluate or quantify the value of each data point according to this acquisition function that we developed before, right? In fact, we said, all right, let's try to keep only the informative data, use the acquisition function. We compute a value for each data point. Literally, for each data point, we have a value. And then we repeat the training, keeping only the first 1% of the most valuable data. And here you see the convergence difference. So this is again the L1 of the log PDF minus the log PDF of the target, right? And you can see the difference between optimal selection of data and random selection of data. And don't underestimate that this is the log scale in a log plot, the difference between the L1 of the logs of the PDFs, right? So this is like whatever you see here as difference is actually a quite dramatic difference at the PDF level. So that actually, it made us feel very happy because, again, with just a fraction of the data, we can actually get reliable models. And again, the interpretation is the same. The error is quantified by, eventually we use a tiny fraction to build a neural network. That way we have some estimation for sigma, and using this estimation for sigma, we are able to quantify the value of its data point. So smart data is better than big data. And of course, the question was, can we understand what this optimal data is, right? So which data is the most informative? And what I'm showing you here, we applied a clustering analysis on actually the full data, right? And we checked from these clusters how close the optimal data are, right? So cluster number one, the clusters that you see here, this is for temperature, and they are arranged according to the frequency of occurrence. So cluster number one appears 24% in 24% of the data, number two is 16.92, and so on. And here also I have the frequency of all data for each cluster by month, colored by month. So you can see that cluster number one is the cluster that appears most often in my full data set. If you look though on the optimal data set, things are very different. It's cluster number 5 that is the most important if you want to predict extreme events. And why this is, like, we are collaborating with, all this work is in collaboration with PNNL, the climate group of Ruby Lung. So Ruby and her colleagues immediately saw that this is a blocking event, and that's why it's important, of course, for training. But now we have an automated way to recover that and say, okay, this is the most important data point or set of data points in your full data set. So this essentially closed the story for the value of data and how we can apply machine learning on correcting operators. And I don't know if I have enough time. I will try in 5 minutes to summarize some of the work we've done on applying these ideas on optimization. And essentially, we extend what we did by combining the acquisition function I just described with the exploitation part, that is to minimize a certain quantity of interest. That gives you Bayesian optimization type of acquisition functions. So these are the standard ones that you can find in the literature, in the graded values reduction, lower confidence bound. And again, they combine the exploration part, like minimizing uncertainty, with maximizing your quantity of interest, right? So all the criteria I just described, they can be extended in the Bayesian optimization context. And we applied in standard, benchmark problems that people are using in Bayesian optimization, and we saw that they actually have the best performance consistently. And eventually we apply this approach on an active flow control problem. So this is joint work with Bernd Noack, and where they have some really nice experimental facilities. So this is an open loop control problem. You see they have a turbulent jet, and they have 6 perpendicular mini jets that they can actuate on demand. And the question is, how should they do that? Like, they have 6, as I said, mini jets. Each mini jet is controlled by this specific, control law. This is open loop. And eventually they have 2 parameters, one phase and one amplitude, that define when these jets are going to be activated for each jet. So 2 times 6, 12 parameter space. Objective function is mixing downstream. So we essentially integrated this idea of active sampling in this 12-dimensional experiment. And each experiment that it was eventually run, it was after optimizing the acquisition function. So here you see the loop. We select the next best point, we perform the experiment, we've met the data set, we update the surrogate model, and then we repeat, right? We use this surrogate model to find the best informative point. So this is a comparison, and Bernd has done a lot of work in the past using genetic algorithms, and we have actually much better performance with genetic algorithms, order of magnitude less experiments. Here I'm showing only Bayesian optimization results. These are some standard criteria: expected improvement in the graded values reduction, and the likelihood weighted is the criterion that I just described. Not only less experiments, but also better optimal. And this is the optimization landscape, again, unfolded in a two-dimensional proximity map. As I said, also it's performing much better than genetic programming. So in that sense, we were very satisfied. And here you can see the optimization landscape for each of the three methods. Interestingly, there is, like on the left, you can see the uncontrolled experiment, how the jet looks, and on the right, the controlled experiment. And the solution we eventually get, or the optimal set of parameters, it has some really, if you want to go to properties, periodically generated mushroom structures, helical motion, and simultaneously oscillating jet column, and that leads to enhanced mixing rate. So we applied this also to numerous other areas, path planning and optimal sensor placement. I don't have a lot of time to present those, but I would like to close by summarizing. Essentially, I have presented some ideas on optimal selection of experiments in the context of UQ and Bayesian optimization with likelihood weighted acquisition functions. These come with theoretical guarantees for optimality, at least in an asymptotic sense. And if you combine them with stochastic neural networks, you are actually able to go and to solve problems in really high dimensionality. You can even overcome double descent issues. And the next thing was to discuss value of data in the context of climate. Again, you have no luxury to select your data. You have, though, a lot of data. So the question is, how do you find the most interesting ones? And then we also discussed on accelerated Bayesian optimization. We presented an idea on the turbulent Z. So I'm happy to take any questions, and thank you very much for your attention.
Well, thanks, Themis, for the talk. Is there any question from the audience? You can try to speak to the mic in terms of direction. I have a question on the compression ratio you use for when you compress the data from the climate data. You use an autoencoder basically, so you get some latent space. So how did you select that latent space, and how big is it for the problems?
Well, of course, there was a lot of try and error. We wanted, this is, I think, eventually the latent space is of order of 100 dimensions. And this was sufficient if you want to give us the performance we were interested in. So this is if you want the minimum that you can use. Above which there is not much improvement. Let's put it this way. It's standard. They call it. Well, we have the stochastic gradient descent. We also have the graduate student descent. This is GST.
And what was the number of degrees of freedom as an input, the CNN?
For the CNN, we are using the full field as input.
And how big is that?
In a coarse resolution, right? The resolution is the standard one that we're interested in, the one that's generated by the model, and it's 110 kilometer resolution, and we're using everything. That's why I say it's a very expensive problem.
Yeah, and I have another question actually on the nudging term you use. So if I understand correctly, so basically when you train your people net, I think with a nudged solution. So the nudged solution, the nudge term is basically a nudging data simulation method. So it depends on some time scale, basically 1/tau.
Oh, very good question. Yes, yes.
So that's the thing to get. Is that some hyperparameter you have to tweak, or you have a robust way to get it, or maybe some physical reason behind it as a time scale?
So yes. So this is the parameter that you are talking about. Excellent question. So this is the nudging parameter. If you set this to be extremely small, eventually you essentially kill all the dynamics of your course model. It's like you enforce the solution to be identical with your reference solution. If you allow this to be extreme, like if you send this to infinity, obviously this term goes to 0, right? So you have no effect. The value we're using is so that the terms we have, the nudging terms, are more or less one order of magnitude smaller compared with everything else. Essentially, we are trying to, and I mean, things are pretty much robust if you stay within this order of magnitude. Why this is where this is coming from? Because we don't want to pollute the core scale dynamics over short time scales, right? So all the terms that appear on the right-hand side, as I said, they are one order of magnitude smaller. What we are achieving this way is to make sure that over, time scales, 10, time scale units, we will still be close. So it's like a guard that is keeping things close, but we don't want to be completely attached. So it's the recipe is an order of magnitude smaller, basically. That's the idea.
Yeah, I have many more questions on this one, but I don't want to take other questions. So, is there any question from the audience?
I have a question.
Try to speak to the mic.
Can you hear me?
Of course, yeah. Very well.
So if you go a bit farther ahead, where you talk about smart data,
yes,
with the slides, it's not clear to me how you can, like, when you evaluate how good, with this formula here, isn't it based that you already have? Like
yes, this is data that we already have. Yes.
No, but what I mean is, like, you can select how important a point is based on the points that you are already considering to build the probabilistic regression or not?
Very good point. Okay, let me clarify that. So to build the probability, remember, we have a vast data set. To build the probabilistic regression, essentially sigma and y, we are using a very small fraction of the data randomly selected.
Okay, and then based on that small fraction, you are evaluating how good, okay.
Then we're evaluating the value for the rest of the data.
Okay.
That's exactly, this is a good clarification. Yeah. In other words, you don't need to train your model with a full data set to evaluate the value of the data. You can do it with. Yes, go ahead. I can comment later. Yeah.
Yeah, go ahead.
So in those acquisition functions, if you want to do some kind of optimization, would it be a good idea to also take into account the value of y of the point that the prediction of the point that you take? Because here you just take into account the probability, likelihood of this point, but not the possible value itself. But in some applications, you were mentioning that you are trying also to minimize something or to solve an optimization problem.
If I understand correctly, the question is for optimization problems that we also need to take into account the point that we are interested to.
Yes, the value y of x star, right? So,
well, if we do, this is like, that's why when we do optimization for the third problem, we are changing the criteria, and we're not only having the likelihood weighted term, we are also having the actual function that we want to optimize.
Okay, yeah, makes sense.
So this is the idea.
In this kappa parameter, how do you fix it?
Oh, the kappa parameter? This is order 1, but again, we are using the standard recipes for Bayesian optimization. There's no, like on how to balance the optimization or the exploitation term versus exploration. Kappa is typically order 1, and we just set that to 1 if we have no reason to do otherwise.
final questions? Thanks. Okay. Well, thanks, Themis. Thank you very much for giving.
Thank you. Thank you. Again, my apologies for not being able to be there.
For this.